question 16 is about electric fields, and part A is finding the electric field strength E due to the point charge, which is the negative 6.0 millicoulombs, at the position at a distance from there to the electron. So the position R is 0.40 meters. And so if we're trying to find the electric field strength, we're going to use this formula, which is in your formula booklet. So K is known as the Coulomb constant, and that's in the front of your data booklet. And then we multiply that by the point charge, and then we divide by the distance squared. Don't forget to square it, easily missed, which gives us negative, but that just means it's coming into the negative 3.37 times 10 to the 8 newtons per coulomb. So with a show that, you always have to ensure that you're using more significant figures than the one they're giving you. Okay, don't write that kq over r squared equals 3.4. You have to actually show that your value is similar to 3.4. Okay. The second part of the question is asking for the acceleration A. Now, acceleration comes from a force. So acceleration comes from a resultant force. So we're needing an equation that links force, charge, because the electron has charge, and electric field strength. So the electric field strength we've already calculated. If you had got part A wrong, you can use the 3.4. So with a show that, generally you need to use that value in the next question. Okay, so we're going to refer to that one in part B. So we're trying to find acceleration. So I don't know the force, but I do know that force equals mass times acceleration, Newton's second law. So I can say ma is equal to the charge on the electron multiplied by electric field strength. Now I know E, I know the charge on an electron, that's in the data booklet. I'm trying to find A, so I just need to know the mass of the electron. Again, data booklet. So the mass of an electron is 9.1 times 10 to the minus 31 kilograms. The charge on an electron is 1.6 times 10 to the minus 19 coulombs. Again, these are constants. And so I'm going to rearrange for acceleration. QE over m. And then if I put in the numbers, and I'm going to use the number that I calculated for electric field strength, but you can use the one that they gave you. And then the answer is going to be very large, and that's the acceleration. Question 17 is a circuits question, and it's quite long. So we have quite a simple circuit. There's no internal resistance, so it shouldn't be too complicated. We have 3 resistors. There's one in series here and then 2 in parallel. We know that R is ohmic, but P and Q are non-ohmic, so the resistance varies with voltage. First question is show that the current in Q is 0.5 amps. The current in P is 0.4 amps. So the current in P is 0.4 amps, and I need to find out what IQ is. Okay, so the way I'm going to do this is I'm going to put kind of P, Q, total. All right, I'm going to put three headings. Now, I know the current in P is 0.4, and I know the voltage through P. and I can find that by using this graph. So if I go across 0.4 to where it goes, I go down here, and I can see that the voltage, the potential difference, is 1.4. So, and I've done that from the graph. I know that the total voltage in the circuit is 6 volts. There's no EMF, there's no internal resistance. So the total voltage in the circuit is 6 volts. So if we have 6 volts coming out of here, and this one is getting 1.4, like this, okay, then Q is getting 6 minus 1.4. So Q is getting 6 minus 1.4, which is 4.6 volts. Now, if I do the reverse of what I did here, I used the current to find the voltage on the graph. For this one, if I know the voltage, I can find the current on the graph, and that's what they're looking for. So I know that VQ is 4.6, so I'm going to go up here, and I'm going to go across, and we can see that the current is 0.45. Okay, so for the marks, they were looking for you to see, to recognise that you've got 6 minus 1.4 is 4.6. That's what they were asking for. Now, to calculate the resistance of R, which is this one, alright, so they're trying to find the resistance of this. Well, we need to know the voltage and the current. So we know that V over I equals R, so we need to find the voltage through R, and we need to find the current through R. Okay, right, so if we're trying to find the current through R, we know that the total current coming through Q is 0.45 amps. Okay, so that's 0.45 amps. Now 0.4 passes through P, so 0.05 passes through R. Okay, so it's the total current minus the P branch. So that's 0.45 minus 0.40, 0.05 amps. So we know the current going through R. We also know that if there is 1.4 volts going through P, there is also 1.4 volts going through R, because if the charge carriers provide 4.6 volts to Q, then 1.4 is going to go through P if it takes that route, or 1.4 through R if it takes that route. So we know VR is 1.4 volts. Therefore, 1.4 divided by 0.05 is 28 ohms. The power dissipated in the circuit, P equals IV. So we're looking for the total current and the total voltage. We know the total current was the one going through Q, which is 0.5, and we know the total voltage is 6, that's the EMF. Multiply them together and we get 2.7 watts. Right, this one, a number of students struggled with this one. So here's the idea. If we are removing P, let me show you where P is. If we're removing P, the total resistance in the circuit increases, because when you've got resistors in parallel, that actually reduces the resistance across these. So the first thing I'm going to do is I'm going to write, so the total resistance in the circuit increases okay. The effect on that for a constant kind of voltage output from the cell is that therefore the total current decreases. So the voltage across Q decreases because the voltage across R increases. Okay, so if we go back up here, so if this is removed now, let's just do a cross. If this is removed, the resistance across here increases. Okay, therefore the voltage across R increases, which means the voltage across Q decreases, and therefore the resistance across Q also decreases. Question 18 is a projectiles question which moves into a little bit of forces as well. So it's like a mechanics question. So the first thing we're asked to do is calculate the average force that acts on the ball when the football player kicks it. Okay, so I'm just going to go to the most basic equation at the beginning, F equals ma. So the idea is that the foot makes contact. Let me do like an impulse graph. Okay, so this is the force on the ball. So at time 0, the person, let's say the person is coming towards the ball, and at this point here they make contact with the ball. The foot then goes into the ball, deforms it, and then the ball starts leaving the foot and then kind of moves away from the foot at that point. All right, so we're trying to find the average force. Now this is the maximum force when the foot is most in contact with the ball, but the average is going to be the mean of this. Okay, and so we need to find the acceleration. So we know the mass of the ball, we're given that, it's 0.45. We know that the initial speed of the ball after the kick is 19. Now that's after the kick, so I'm actually going to say it's going from 0 to 19. So I'm actually going to say, even though this is the initial kind of leaving speed when it becomes a projectile, I'm going to say the initial speed when the ball is kicked, as the ball, before the ball's kicked, to the speed after it's left the foot. Now I don't know the acceleration, but I can calculate it by doing v minus u over t, and I know the time that the kind of 0 to 19 happens over. And so I'm going to put these in and find my value for force. So 0.45 kilograms times 19 minus 0, that's the change in velocity, and it does that in 55 milliseconds. And so we got 155, which is, to two significant figures, 160 newtons. The ball leaves the ground at an angle of 22 degrees. That means to the horizontal. So what we've got is the ball leaving the ground at an angle of 22 degrees. So if the velocity of the ball is 19, we could, if we need to, I'm not sure if we need to yet, work out the vertical speed and the horizontal speed. So the vertical is going to be opposite over hypotenuse, which is going to be sine, and the horizontal is going to be cosine. So they're there just in case I need them. Okay, it's always good to do that. The ball leaves the ground at that angle. The horizontal distance from the initial position of the edge of the ball to the wall is 11 meters. How long does it take to reach the wall? Okay, so this is the distance, 11 meters. And that is a horizontal displacement. I'm trying to find the time, and time is distance divided by speed. So if I've got a horizontal distance, I need the horizontal speed. So actually this is going to come in handy. So this is uv. And I know that the speed doesn't change in the horizontal, so u equals v. And so I'm going to do my distance, 11 meters, divided by 19 cos 22. Make sure you're in degrees. And I get 0.62 seconds. That is the time it takes to reach the wall. Okay, so it takes 0.62 seconds to reach the wall. Okay, now it might go over the wall, it might hit the wall, but it will take 0.62 to reach the wall either way. We're told the top of the wall is 2.4 meters above the ground. Deduce whether the ball will hit the wall. Okay, so we're now trying to find the height gained in a time of 0.62 seconds. So if let's do our suvat. Sorry, I didn't mean H, I meant V. Okay, so we're looking at the vertical here. We know that the wall is 2.4 meters, so we need to see how our vertical height compares to 2.4 meters at 0.62 seconds into the journey. The initial speed we know, but we don't know the final speed when it reaches the wall. So the initial speed is the vertical one here. So I'm going to put that in, 19 sine 22. And I know that it's going in the opposite direction to gravity, so it's negative 9.8. So I can use S equals ut plus half at squared. Remember, a is negative. So I've got 19 sine 22 times 0.62 plus half times negative 9.8 times 0.62 squared, and therefore I can calculate the height gained at 0.62 seconds, and the height it gains to 3 sig figs is 2.53 meters. So you need to deduce, so it's saying give an answer. Will it hit the wall or not? So I'm going to say 2.53 meters is greater than the height of the wall, therefore no, it will not hit the wall. It's very important that you make it clear that you recognise what your number means for the outcome. In practice, air resistance affects the ball. Outline the effect that air resistance has on the vertical acceleration of the ball. Take the direction of the acceleration due to gravity as positive. Okay, so the direction due to gravity is positive. So if the ball is moving down, it has a positive acceleration. If the ball is moving up, it has a negative acceleration. Okay, and gravity is positive already. So when the ball is moving upwards, so if the ball is moving upwards, the force due to drag is opposing the motion, therefore the drag will be positive. So if the ball is moving upwards in the negative direction, drag is going to be in the positive direction. Therefore, we've got the idea that the force due to gravity plus the force due to drag is going to be more positive. So therefore, the acceleration is greater than g. Okay. It's going to be the converse for downwards. So if the ball is moving downwards in the positive direction, drag is negative. Okay. Therefore, the force due to drag, which is negative, plus the weight, which is positive, is going to be less positive overall because we are minusing drag. Therefore, the total acceleration is going to be smaller than the value of gravity. Okay. You do have to be explicit about how you've got your drag directions. So drag opposes the direction of motion, and it's important that that's clear somewhere. Okay. And then D, we've just put a little bit of circular motion in there. We're trying to find angular velocity. So before we worry about a formula, I'm just going to write down the numbers. So we've got a horizontal velocity. We've got V. We have a radius of 0.11 meters, and I'm trying to calculate omega. Now, if you would, some people struggled with this, but I would argue if you'd actually written down the numbers and the terms that you've got, and then what you're trying to find out, if you'd looked in your data booklet, you would have found V equals R omega. So V over R equals omega. 1.4 over 0.11, 12.7, and you need the unit, and that is rad per second. Okay, or you could have just said per second. Okay, so as my final answer, I've said is approximately 13 rad per second, or you could have just said per second. Either of those is fine, because if you don't write the term rad, it's taken as given in an angle. '19 was done very well. We've got a planet orbiting a star, so we've got an orbital motion, and we're told various data bits about the mass and distances of the planets and stars. So part A is saying, explain why a centripetal force is needed for the planet to be in circular orbit or circular motion. So I've said the resultant force acts towards the centre of the circle. Of a circle, in other words, the orbit. Okay, so it's acting towards the star. Otherwise, it will go off at a tangent. Okay. Now, the reason that comes about is because you have a changing velocity at all points of a circle. And a changing velocity means acceleration, and acceleration leads to a resultant force. Okay. Saying calculate the value of the centripetal force. So F, we know, is normally mv squared over r, but we don't know the speed of the orbit. We're not told that. We're told the distance of the orbit, we're told the mass, but we're not told the speed. So we can't use that, but we do know that in an orbit, the forces from centripetal and gravitational are they're equal. So if the centripetal is greater than gravitational, it's going to go to a higher orbit. If gravitational is greater than centripetal, it's going to decay its orbit. So these are equal. So therefore, if we can't use this one, let's use this one. And this we can do, because we know the mass of the planet, the mass of the star, and the radius of the orbit. So the mass of the star is 3.2 times 10 to the 30 kilograms. The mass of the planet is 8 times 10 to the 24 kilograms. And we know the radius of the orbit is 4.4 times 10 to the 10. So, and we know that G is 6.67 times 10 to the minus 11. So if I put those numbers in, remember to square R, the number you get, I'm not going to write it all out, is this. Okay, but remember to square R. For C part 1, we're asked to calculate the gravitational potential due to the planet and the star. So we need the potential due to the planet at the surface of the planet and the star at the surface of the planet. So lots of people used the right formula for this, but not everybody recognised what they actually had to do in terms of planet and star. So lots of people calculated the potential due to the planet or the star, but you actually have to add them, okay, because it's saying and. So we need the potential of the planet and the potential of the star. Only when you do that do you get a number that is particularly close to 5. So the potential of the planet is negative g mass of planet over radius of planet. Okay, and that equals negative 5.9 times 10 to the 7 joules per kilogram. The potential due to the star is negative g mass of star and then radius of planet around star, so it's the orbital radius, so that's what we were looking at there. And we've got 6.67 times 10 to the minus 11 multiplied by this divided by the orbital radius, So the connection between the planet and the star. I forgot to say, actually, you need to be careful here. So it's 10 to the 6. They were a bit sneaky, and they said here it's 10 to the 3 kilometers. And of the papers I marked, some people fell into that trap. So it's actually 9.1 times 10 to the 6 meters you had to convert, and that was very mean of them to slip that into the information given. So if I do that, I get negative 4.9 times 10 to the 9, which I grant you is close to negative 5, but we can get it closer. So the total is Vp plus Vs. So it's negative 5.9 times 10 to the 7 plus negative 4.9 times 10 to the 9, which equals negative 4.909 times 10 to the 9 joules per kilogram. Okay. And then the final one was escape speed. So we know that V escape is equal to 2gm over r, but we've been using this bit of the formula for the previous question. So we know that gm over r is the potential. I'm going to put V grav so you don't get confused with the V's and the V's. Okay, again, notice it's a show that question. Oh, sorry. It's not working. So it's a show that question, which means you are going to need that part of the question in the next bit. So we're going to need that number. I'm going to use the number that I got, but VGrav is basically your 5 times 10 to the 9. Okay, show that means you need to be ready to use it in a later part of the question. So it's root 2 times either that one or that one. I'm going to use mine, but either way I think you should have had a very similar answer.